we'll do is I want to go back over the lab, the VLAN T-shoot lab. Did anybody attempt it or?
Yep.
Yeah.
Good stuff. A few. Okay. There's tumbleweed there going around. I was like, okay. But we'll have a look at it first. So basically, it's, you can see what it says here. It's similar setup that we had before, a router on a stick. So this is our kind of a design, and we have a VLAN PC, VLAN 2, server VLAN, VLAN 3. We have divided 0/0, the router port 0/0 into two subinterfaces. 0/0.2 should be VLAN 2. 0/0.3 should be VLAN 3. The switch port is 0/2. The device connected to 0/2 is in VLAN 2. So this is Bob, whilst the web server is on 0/3, which is VLAN 3. So when it's finished, if it all works, 192.168.2.5, Bob here should be able to connect to the web server 192.168.3.5. Any questions? All right, okay, let's get cracking. All right, so again, where do you start? Check the PCs first, maybe. Then check the switch config and then check the router config, because it could be anywhere. Follow the path. So log in, go into the IP config of the PC here. Bob 192.168.2.5, 255.255.255.0, 192.168.2.1. So the IP address looks okay, yeah? Then check the PC, the server, 192.168.3.5, 255.255.255.0, 192.168.3.1. Okay, so there's no nastiness there that we had last week with the, remember we had one wrong IP address. That seems to be okay there, yeah? So the issues are with on the switch here itself and on the router. How far can we get? Can I ping my default gateway from my PC? Or can Bob ping his default gateway from his PC? Ping 192.168.2.1. No, okay. So we can't get as far as our router. Okay, we'll log on to the switch. Let's go in here. Now we did say the details on the switch, they're gone offline. But we know the ports, 0/2 VLAN 2, 0/3 VLAN 3. Let's have a look. Show VLAN. Any problems there?
VLANs are the wrong way around.
Yeah, they're mixed. 0/2, the physical port of 0/2 is in VLAN 3. The physical port of 0/3 is in VLAN 2. So we need to swap them around. Now, I suppose there's no really easy way to do it. You have to go into the interface and remove the VLAN and add it back in again. Okay. So VFace T interface FA 0/2 switch port access VLAN 2. That will take it out of FA. That will take it out of VLAN 3 and put it into VLAN 2. Int FA 0/3 switch port access VLAN 3 and switch over VLAN. Looks a bit better, yeah? PC VLAN 2 connected to FA 0/2. The server VLAN 3 connected to FA 0/3. Okay. Anything else there? Any other problems?
The trunk.
Yes. Look, FA 0/1 is meant to be our trunk link, and it's in the show VLAN config. If you do a show VLAN, you shouldn't see your trunk link in there. Okay, so that means the switch thinks FA 0/. That means the switch treats FA 0/1 like an access port. show interface FA0/1 switch port. And operational mode. As I say, administrative mode, dynamic auto. So it's just down. So it's not doing anything. It's defaulting anyway to an access port. So we need to change that. So again, config space C, interface FA0/1, switch port mode, access even. Change it. Just hard code it. Oh, what am I doing? Into FA0/1, switch port mode trunk. Jesus. Now we do show VLAN. Oh, something's wrong there. FA0/1. Let me just go in here again. Is this right? Let me see. Go in here, config space T, int FA0/1. Let's shut this down here first. No, shut down. Okay, my bad. There's a problem there, right? There's nothing connected into FA0/1. I was wondering because we're seeing the link down. So it's gig 0/1 here. Must be. So exit. But gig 0/1 is also seen as an access port. Let's check this out. If I int gig 0/1, shut down. Okay. The int port, the gig, we had a connection to gig 0/1. I should have put a gig connection in there. So do no shutdown again there. Bring it up. Just fast forward that there. Okay. So if I go into the switch again and I do show interface gig 0/1, actually space switch port. I only want to see information with the switch port here. And you can see in here, operational mode is a static access. So we need to change it to a trunk link. Config space T, int gig 0/1, switch port mode trunk. Okay. See what happens here. Exit, show int, I should show VLAN, and gig 0/1 is gone. The connection now is gone. It's gone from the show VLAN command. What command do you use to find out whether it's a trunk or not?
Show trunk.
Show interface trunk. Near enough. There we go. Gig 0/1 is on, trunk in 802.1q, and the native VLAN is VLAN 1. Again, the native VLAN is basically if a switch receives a frame for any VLAN except for VLAN 1. So if a switch receives a frame for VLAN 5, it will send that frame out to trunk link, and it will put a tag in on the trunk port to tell its neighbor that this is for VLAN 5. It will do that for every VLAN except for the native VLAN, which is VLAN 1. So it won't add in this little tag, this sticky note. I compared the tag last week to a sticky note to tell the other neighbor switch what VLAN this frame is going to. Okay. So you can verify it by doing a show run, really useful. Okay, and just having a look. Interface gig 0/1, switch port mode trunk. And then you can go into the specific, let's have a look at the VLANs. Show VLAN, show VLAN, and there you have FA0/2 and FA0/3. Okay, And they should have been in the ports of config. Yeah, there you are. Switchboard access VLAN 2, switchboard access VLAN 3. Okay, cool. So let's see if we can ping our default gateway now. No, something's still happening. Okay, so we need to go into our router, find out what's wrong. CLI, enable. Now there's different commands you can do. You can do a show run. Show run will show you your overall, but we want to really just focus on 0/0. So you could do show IP int brief. And you can see our 2 gig 0/0 is split into 2 subinterfaces. Gig 0/0.2, gig 0/0.3. Anything wrong with that?
.1 is administrative down.
That's fine, because remember the two we've only got one link here active. This one physical port 0/1 is going into 0/0, and 0/0 is being divided into sub interfaces. So we're not even using gig 0/1.
There's no IP address.
There's no IP addresses. There's no IP addresses. So remember 0/0.2 is the default gateway for VLAN 2. It should have an IP address. 0/0.3 is the default gateway for VLAN 3. It should have an IP address. So we need to put in an IP address. Okay, but before we do that, let's just another command. Let's just do a show run here. Anything else in there?
Encapsulation, the .1 queue is 3 for .2 and .2 for
Yeah,
.0.3.
they're swapped around, yeah. So some idiot, me, has put this sub-interface 0/0.2 being supporting VLAN 3 and 0/0.3 being supporting VLAN 2. So we need to swap them around. We need 0, because the diagram said 0/0.2 is for VLAN 2, 0/0.3 is for VLAN 3. Okay, so we have to do, so change these two here. So go back in, config space T, int gig 0/0.2, no encapsulation. Or actually, we can write over, it should be able to write over, encapsulation.1q space 2. Okay. We have to remove it. So no encapsulation.1q space 3. Encapsulation.1q space 2. Okay, what it's saying is you can't have the same VLAN ID on 2 interfaces. So I need to go into 0/0.3 and remove it from VLAN 3. Does that make sense?
Yep.
So exit int gig 0/0.3, no encapsulation .1q space 3. Now, if I do exit, show run. So basically, I've removed encapsulation.1q from VLAN for the respective VLANs. So I have to add them in a new IP address or an IP address in for 0/0.2 and an IP address for 0/0.3, which would be the default gateway. Is there any questions on that, guys?
Nope.
Okay, cool. So config space T int gig 0/0.2 encapsulation.1q space 2. Now give that an IP address. IP address 192.168.2.1. 255, 0. Exit. So again, I'm going into this sub interface int gig 0/0.2. That tells the router, the dot there tells the router I'm creating a sub interface. I'm giving it the number of 2. It can be any number at all. It just makes sense to use a number of 2, okay, to match the VLAN ID. The next one is where you actually match. This is where you logically match the sub interface 0/0.2 with VLAN 2, and then this is where you give it an IP address. So to do the same thing for a 0/0.3, int gig 0/0.3 encapsulation that 1 q space 3 IP address 192.168.3.1 255.255.255.0. Okay. Show IP int brief, and there you have it. 192.168.2.1, 192.168.3.1, and I think we're ready to go. I think so. So can I ping my default gateway? Yeah. We get a response. Can I ping the server's default gateway? 3.1. Yeah. Getting a response. And can I ping 3.5? And there we go. So all good. It seems to work, yeah. Okay. Any questions on that, guys? Right. We'll move on.
All good.
So let me just. Yeah. Now there is the actual if you go in, there's the VLAN troubleshoot solution is in there as well. So you can actually go back over the notes there. So basically we had to go in, interface, create our switch ports. Sub interface were wrong. And our interface and our connection here, gig 0/1. Yeah. So there are our 3 issues. Well, not our 3 issues. Well, this is 1, this is 2nd, and 3rd. Okay. Cool. All right. So moving on. Let me just see where we are in this. Okay. Just going to open this with Paint. Okay, so there looks to be a little bit going on here. Okay, just ignore this for a second here. Just concentrate on our diagram here, right? So here we have 2 connections, right? We have a link here, switch A. Let's kind of call it switch A here. Let's give this an A, and switch B here. And you can see switch A has a connection to Tom on 0/5. And it's got 2 trunk links. One trunk link on port 0 going to switch B on port 0. Yeah. And then you've got another connection, port 1 on switch A is going into switch B on port 1. So here it looks like we've got 2 active connections at the same time. Yeah. So this link here and this link here. That's usually for redundancy, because now, redundancy is good. So again, redundancy is 2 different ways to get to the same device. That if one connection, this link here between A and B, let's say this connection went down, well, then all traffic between Tom and Bob will go across port 1. Okay, so that's good. But let's say, and let's just have a look at the way switches forward out broadcast, right? So let's say Tom is sending a ping to Bob. And the source, let's say it's a broadcast. Yeah. So let's say Tom's MAC address is A. And the destination is F. So what I'll do is, let me just make the broadcast a little bit smaller. Okay, let's make this a little bit smaller here. Okay, so let's say Tom sent this broadcast message. Now the way switches deal with a broadcast message, you can see it over here. So by default, the switch will send out broadcast at all ports by design. Yeah. So if a switch receives a broadcast frame, and the switch will know it's a broadcast frame because it'll have what FFFFFFF in the destination header of the MAC, the switch will send that frame out all ports except the port on which the frame came in on. Okay, so the switch will send this message. Oh, let me just remove this. So this Tom is sending the frame. It's going to go into the switch on port 5. Then the switch is going to see it and say, okay, well, because I'm a broadcast, I'm going to flood this frame. Because it's a broadcast message, I'm going to flood this frame out all ports, except the port on which the frame came in on. So where did this port, what port did this frame come in on? Tom sent it, so it came in on port 5, yeah? So what's it going to do? It's going to flood this frame out all ports. So it's going to send it out port 1 and port 0 at the same time. Okay, so let's just concentrate on port 0 for a second. So this frame is going in along the trunk link on port 0. It gets to switch B on port 0. Switch B will then look at the destination MAC address and say, okay, this is FFFFFF. What do I need to do? I need to flood this frame out all ports except the port on which it came in from. So this frame here came in on port 0. So switch B says, I need to send it out port 3, and I need to send it out port 1 again. So this frame now is going back in to switch A on port 1. What's the switch going to do? Because this came in on switch 1 on port 1, it's going to send it back out port 5 and back out port 0. Do you notice a pattern? What's happening? We have a
Loop.
A loop. What type of loop is it? It's a layer 2 loop because there's switches here. This is a layer 2 loop or broadcast storm. You wouldn't have this issue with a router. Why not?
Doesn't broadcast.
Exactly. So if you had a switch here and you had a connection to a router, and even if you had 2 links, let's say you have 2 active links here. So this one is active and this one is active. The switch sends a broadcast message, comes in here. The router is just going to kill it here because routers do not send on broadcast messages. Let's just close that again and go back in. Why are we having the broadcast storm? What's causing the broadcast storm here? We're having the fact that we have 2 active connections at the same time. We've got port 0 to port 0 on the switch, port 1 to port 1 on the switch. Two active links at the same time. So when a frame is coming in, again, say this is broadcast message. When this broadcast message comes in, it's going out port 0 and it's going back out port 1. Around and around and around and around. Let's say this way, let's just put it this way. If I remove this link here, would we have a broadcast storm?
No.
Yes.
No.
You know, yes. Again, the reason why we're having it is because we have two active connections. So let's look at it again. Let's have it comes in. What's the switch going to do? It's a broadcast. It will send it out port 1, or sorry, port 0. Switch B receives it. What will switch B do? Will switch B send this out back out port 0? No, because switch B will send it out all ports except the port on which it came in on. So it won't send it back to switch A. Switch B will not send it back to switch A because it came in on port 0. Does everyone see that? So a broadcast storm happens here when you have two active trunk links between the two switches. That will mean that this frame will go around and around and around and around because of our two active connections. You remove one of the redundant connections and you stop your broadcast storm from happening. It's very important that people see that. Any questions on that at all, guys? So a lot of people being quiet. So I like, let me know if you understand that. Let me know if you want me to proceed.
If a switch detects a broadcast storm, will it disable any of the ports?
No, the switch won't know what a broadcast storm is because the broadcast message is going so far or fast around that, but basically you brought like when you have a broadcast storm, okay, you can do ARP inspection packets, which will stop it, but it's really not. You're not going to see it on your CCNA. So at more advanced Nexus stuff, you would see it. So if so, to answer your question, if this was a CCNP course, yes. But it's a CCNA, so no.
What does it actually look like though in like practical sense? Like Tom tries to ping Bob, broadcast storm is in place. What happens? Like
I'll show you later on.
Cool.
Basically, nothing will happen. Nothing will happen is no traffic is going to get through because what will happen is this message is going around so fast that no other traffic is going through. Like switches can send millions of frames out of its port in a second. So they're so efficient at sending these broadcast messages that they're nearly too efficient. Like they're sending them at wire speed. Okay, so I want to go back to the reason why are we having this broadcast storm? The reason why we're having the broadcast storm is because we have two active connections between switch A and switch B. Not only two active connections, we've got two active trunk links. Remember, your trunk link is your special switch-to-switch connection. So Tom here, again, generates a broadcast message, and you're probably saying, oh, broadcast messages don't happen very often. They happen all the time. In fact, for Tom to ping Bob, Tom needs to know Bob's MAC address. How does Tom find out Bob's MAC address? It has to send an ARP. An ARP is an example of a broadcast packet. So these happen all the time. So again, let's just do this too again. Does that make sense? So it goes out port, it port 0. Bob will receive it. It'll send it out port 3 and back in port 1. Think of it just as a loop. You have a loop here. Just going round and round and round and round. If you remove the loop where you've only got one connection, you stop the broadcast storm from happening. Okay. Now the good news is that obviously there's a measure, switches have a design put in to prevent that from happening in the first place. And it's called a spanning tree. Okay. And what spanning tree will do is switch A and switch B will notice, will identify that there's multiple connections between the two switches. And I'll talk about how it is. I'm going to give you, what I'll do is I'm going to give you an overall view of spanning tree, and then we're going to do a deep dive into it. Okay, so switch A and switch B, see, there's a loop here. There's trunk connections between 0, 0, 1, 1. Okay, and switch A and B will then decide amongst themselves to essentially bring down one of the links. Or shut down, place a tree, if you like. Think of spanning tree as in the link is here, but it'll actually put a tree here to block the packets. So any connections, any traffic between A and B will only use port 0. So it's blocked this road, if you like. You can't have port 0 to 0 and port 1 to 1 active at the same time. If you do, you're going to have a broadcast storm. So what happens now, any traffic between Tom and Bob is only going to go out port 0 all the time. Okay? Until something happens on port 0. So if port 0 goes down, the link goes down for whatever reason, dodgy cable or dodgy NIC or dodgy SFP or maybe fiber issue, dirty fiber or something, then the connection on port 1 between A and B will automatically be established. So the whole point of this is I want you to understand what spanning tree is that you can't have active connections between two switches at the same time. Okay, you can't have 0 to 0 and port 1 to port 1 active at the same time. So what spanning tree is there to do is to temporarily disable one of the ports in order to stop this broadcast storm from happening. So it'll disable one of the ports. Let's go back. Now it's done it on switch B, port 1. You can see the link down. So if you know, so there's no traffic is going to get between A and B on port 1 because this port is down. It only takes one disabled port to stop traffic going between A and B. All traffic between Tom and Bob will now go over port 0. Okay, so logically it's like this link is down, it doesn't exist, right? This is the logical connection. All traffic between Tom and Bob goes down until something happens to connection on port 0, like it goes down or gets unplugged or something. When that happens, the link the connection on between A and B on port 1 that was already there, physically there, gets logically established and logically turned on, and then all traffic will go between Tom and Bob will go over port 1. Is there any questions on that? I'm sure you have loads. Let's go into it a little bit more. See how it works. Okay, no, that one. Go into this one here. It's best to explain spanning tree when we look at 3 switches. It's easier. First of all, do we have redundant connections between switch A, B, and C here? Have we got redundancy? Yes, we have. Don't we? If we have a look here, we have a loop. We have a danger of being a loop. So let's go here again. Let's draw a quick packet, right? And source is a destination is FFF. Okay, so if we have these 3 links at the same time active, right? This link here is active, this link here is active, this link here is active. Well, then a broadcast message, let's we have a PC over here connected into switch A or switch 1. And this PC generates a broadcast message. PCs are constantly generating broadcast messages all the time. This broadcast message is going to go into switch A or switch 1. Switch A is going to send it to switch 2. Switch 2 will send it out to switch 3. But because switch 3 has a link back to switch A, it's going to send it out this way. It's going to go round and around and around and around and around and around and around. You got a layer 2 loop, you have a broadcast storm. Now let's say, for example, we remove this link. Do we have an exact, will we have a layer 2 loop now? Will we have a broadcast storm now? The PC generates a broadcast message. It goes into switch 1. Switch 1 will send it to switch 2. Switch 2 will send it to switch 3. Switch 3 will not send it to switch 1 because this link, let me just remove these red arrows, it's a bit misleading, does not exist. Physically, it's still there, but logically, all traffic between switch 1 and switch 3 is suspended, is shut down, or is disabled because of spanning tree. Spanning tree was invented when switches really just came out as bridges. It was invented by a woman called Radia Perman. She used to work for Digital. And it's an IEEE standard. So it's an IEEE standard 802.1d. IEEE 802.1d. IEEE meaning you can have a Cisco switch here. Sorry, writing is terrible. Cisco connected to a Juniper, and it'll work. They'll talk to each other. They can have a little, yeah. So, okay.
If the link went down, if the physical link went down on FA101 between switch 2 and switch 3.
If the link is down between switch 2 and switch 3,
as in say for example, if the cable was damaged or the NIC or
yes,
obviously between switch 2 and switch 3,
yeah.
And then if the link then between switch 1 and switch 2 was enabled, but it won't send the broadcast back on the port, it sends out obviously with.
Okay, so if this link is down now, well, so what will happen is that switch the link between switch 1 and switch C will come back up.
But if the broadcast message goes out on switch 1,
and
then it comes into switch 2,
yeah,
it won't go back up the same port. Switch 2 back into switch 1, correct?
Okay, let me just, there's something wrong here with my, let's do it. What is wrong with this song? F11 maybe. Let me just close out of that paint there. Sorry, there's some issue there with it. 1 second, I'll go back in. Why is it doing this?
Is it the little down arrow beside the
Yeah.
question mark on the right-hand side?
Top right.
Top right, is it?
Yeah.
That's it. Jesus Christ, thanks. Here we go. Right. Okay, so what were we asking for? Right. So sorry, what was the question again there?
See if the physical link goes down between switch 2 and switch 3,
Right.
and
Okay.
then we're saying that the broadcast message won't go back in on the same port it came out on.
So let's say, right, let's say switch 3. Now, spanning tree, first of all, is automatic. It happens all, so
Oh, see, yes, yeah.
there's no human intervention at all. So you connect these 3 switches together, spanning tree will do its thing behind the scenes. Okay. So what will happen is, let's say, for instance, it will disable this connection here. Okay. So no traffic will run between A and C. This link, it's like if we have a PC here, Tom, and he wants to speak to Bob. Where is that going? Where is the connection between Tom and Bob going? Through switch 2 and on that way. You can't have these 3 active connections at the same time. If you do, you're going to have a broadcast storm and no traffic will get through. So what spanning tree's job is to temporarily shut down one of these ports, disabling our loop. When you have your loop disabled, all traffic between Tom and Bob, for example, or all, like I'm only like, so all traffic between Tom and Bob will go from switch 1 to switch 2 to switch 3. They can't go from switch 1 to switch 3 because you can't have this link, and this link active at the same time. You cannot have those 3 connections active at the same time. If you do, you're going to have a broadcast storm within seconds. How is that? Is that just, do you understand the reason why you would need spanning tree?
Yeah, no, I get it. Yeah, I see it there now. I see it, yeah.
Okay, cool. Agert, you're okay. Graham, sorry, Edmund, John, Liam, Philip.
Yep.
Okay, cool. Right. So as long as we know why we need some mechanism in place to prevent our broadcast storms from happening in the first place, let's talk about this spanning tree process. Right. There's a special frame called a BPDU, and the job of the BPDU is to manage your spanning tree process. Okay, BPDU stands for Bridge Protocol Data Unit. It's a layer 2 frame, so it operates at the data link layer. Okay, and it's sent out all the ports every 2 seconds. Every 2 seconds. Okay, just say hello, hello, hello. Just think of it as an envelope. This BPDU. Now, part of this BPDU contains what's known as the bridge ID. Okay, and the bridge ID is a default number of 32768 dot the switch's MAC address. Okay, so switch A is going to be sending this broadcast message or this BPDU of 32768 AAA. That's switch A's BPDU or bridge ID. Switch B's bridge ID will be 32768 BBB. Switch C's bridge ID will be 32768 CCC. Okay, and this will be going around every 2 seconds. So switch A is going to be sending it, switch B is going to be sending it, and switch C will be sending it. Now, from this bridge ID, from this number, 32768 AAA or BBB or CCC, a root bridge is elected. Okay, and the root bridge is simply the best switch or the core switch. So, okay, the election process, it kind of says, I want to be the best switch. Now, it doesn't have to be the best switch. Okay, we're just going to say it's the best switch here. So from the bridge ID, a root bridge is elected, which is the core switch. The other switches will also elect the same switch. So you'll have one bridge ID, or you'll have one root bridge. Let's say this switch here. Switch 1 is root bridge. The other switches must find the best path back to the root bridge. So switch 2 will find its best path back to the root bridge. Switch 3 will find its best path back to the root bridge. And any redundant link will be temporarily disabled. And there is a rule for spanning tree, and it is lower is better. Lower is better. The lower, the better. What do we mean? Well, in the election process, we have these numbers. Bridge ID of A is 32768.AAA. The bridge ID of B is 32768.BBB. The bridge ID of C is 32768.CCC. Okay, so we've got 3 different bridge IDs. How is the root bridge elected? Lower is better. So the bridge ID starts off, how spanning tree elects the root bridge, it looks at the numbers first. This priority value of 32768. Now there's a tie between A, B, and C, okay? Because 32768 is 32768 is 32768. Switch A, switch B, and switch C. So how it, does that make sense? So it looks at the lowest priority value first, which is 32768. So by default, that's the number that hasn't changed. So the kicker is going to be the switch's MAC address. So in terms of here, which is going to be elected to root bridge? Switch A or B or C?
A.
A, yeah, because A is a root bridge. Because AAA is lower than BBB and is lower than CCC. Okay, so switch A, just on that, that's the only thing that elects A as root bridge. It's the only value that elects A as a root bridge. So switch A goes, okay, I'm the root bridge, okay? And then switch B says, okay, I have to find my best path back to the root bridge. Now, where do you think switch B's best path back to the root bridge is? Is it going out FA0/0 or 1/0?
1/0.
On switch B?
Well, it can't go back out on the same port it came in on.
No, we're not. Okay, we're not talking about we're not talking about traffic at the moment yet. We're just talking about this spanning tree election. So let's say switch B is here and switch A. So all we have done is said A is the root bridge, right? A is the core switch. Then switch B says I must find what is the best path from switch B to get switch A.
Like him.
It's the connection, the one that's directly connected. It's quicker, isn't it? If you think about it, it's going to take less packets for switch B to get to switch A. When it's direct, then going via switch C. And the same with switch C. Switch C's best path back to switch A is out FA0/0 as well. Okay, so the switches are sending these messages every 2 seconds, called a bridge BPDU. And there's a priority value of 32768. That's the switch's MAC address. From the bridge ID, a root bridge is elected, which is the core switch. What was the root bridge? Switch A was the root bridge. Why? 32768 AAA BCCC is lower than so switch A is, yeah, because AAA is lower than BBB is lower than CCC. Okay. Now we're here. All the other switches must find their best path back to the root bridge. So in other words, switch 2 here says my best path back to the root bridge is the direct connection here. And switch 3 says my best path back to the root bridge is out 0/0. So where is our redundant connection?
FA1/0.
On both switches, exactly. So FA1/0 is temporarily shut down. So what spanning tree will do is it will logically disconnect this connection. Because you can't have the 3 active connections at the same time. So if you have a laptop here in switch B, and you have a laptop here in switch C, how are they going to talk to each other? Through the root bridge and down. All traffic will go between B and C, will go via A.
Oh,
yeah.
So could switch 2 or switch 3 become?
What's that?
Oh, sorry, could switch 2 or switch 3 become the root bridge if switch 1 sat down?
Yes, they can if you configure it. Yes, yeah. Yeah, they can. What will happen? So at the moment, right, this port is shut down on switch 3. So like I said, if we have Tom and Joe here, say this is Tom and this is Joe over here, any packets between Tom and Joe will go via the root bridge and down. If something happens, one of these links, this link goes down, well then what will happen? The connection between B and C will automatically be restored. This will come up. So you still have your 2 active connections here, but you just can't have 3 because you're going to have a loop.
In that scenario, does switch A still stay as the core switch?
In this scenario,
Switch
switch A will stay as a core switch. Yeah. The link here is down, but it'll stay as a core switch until, and what will happen if this link goes down here or this link comes back up, this port then gets shut down. We'll see this happening out. We'll see this. We're going to do a few labs on this, so hopefully it'll get clearer. Okay, so here's a question, right? Make this a bit bigger. Maybe use your chat here. Just give us a second. Which switch would become the root bridge? So use your chat. A or B or C. If you don't want anybody copying your answer, you can send it privately to me. So which switch? Is it switch A would become the root bridge? assuming that the priority value is 32768 for all three switches. So what switch is going to become the root bridge?
Oh, he's on. FF 1, 2, sorry.
Take your time.
No. C.
Remember, lower is better.
D is lowercase in 67. A, B, C, E, F 69. C.
Okay. So fair play. Yeah, I think he's a, yeah. We're all in agreement that is switch C. Yeah. So again, remember, lower is better. So it starts off with 32768, and then it looks at here, 8D67, 8D67, 8D67. The same. FF, FF, FE. Here. E is lower. FE69 is lower than FF23, is lower than FF21 or 12. Okay, so it starts at the left and it goes across. Remember, hexadecimal characters go from 0 all the way across to F. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F.
Assume that the 8D67, the capital D and the lowercase d doesn't make it.
Doesn't make any difference. It's the difference. It's the same as like having a lowercase 3 and an uppercase 3, because a D here is, it's a number. Yeah. It's a number. What D is? What number is D?
14.
13. Yeah. We will go. When is this? Yeah, when we look at IPv6, we'll talk about converting from binary into decimal into hexadecimal. It's not too bad. Well, yeah. Okay. All right. Where were we? Go back here again. Okay, so go back here. This was our diagram. So we said that the switches are going to be sending out these BPDU messages. Okay. From the BPDU, you've got the bridge ID. You can see the bridge IDs here. Switch A's bridge ID is 32768 AAA. Switch B's is 32768 BBB. Switch C is 32768 CCC. So from the bridge ID, a root bridge is elected. So you can see switch A here says, oh, I'm the root. I'm the best switch. Well, then switch B says, I must find my best path back to the root bridge. And C says, I must find my best path back to the root bridge. Now, how do the switches elect their best path back? They have what's known as a costing system, okay? They have a costing system. So the costing system depends on the speed of the link. So if you have a 10 meg connection, then the speed of the link or the cost is 100. So you got speed and cost. Speed or bandwidth and cost. If you got a 100 meg link, which is fast Ethernet, that has a cost of 19. This is a cost of 100. If you got a gigabit connection, that has a cost of 4, and a 10 gigabit connection has a cost of 2. So 10 meg has a cost of 100. So what's the cost for B to get to the root bridge directly?
$19.
19. Yeah. So B says it only looks at one link. It looks at its own link here. So B says my FA0/0 and FA0/0 has a cost of 19. So therefore, for B to reach A directly has a cost of 19. Now, what's the cost for B to get to A via C? The cost of B to get to A via C. You got 19 here.
So 19, is it?
And well, 19 is for B to get to C. But what's the cost? Because it's cumulative. What's the cost for C to get to A?
19.
19. So then what's the cost for B to get to A via C?
19.
No, for B to get to A via C.
38.
38. Yeah. Let's think of like if you have like Galway, Athlone, and Dublin. Let's say Dublin is 100 kilometers from Athlone, and Athlone is 100 kilometers from Galway. What's from Dublin to Galway via Athlone? 200 kilometers. Kind of just adds it up. Same here. Does everyone see where we're getting the 38 from? The cost for B to get to C is 19. And for C to get to the A is 19. Because you look fast Ethernet, these are the speeds. Remember the rule with spanning tree. Always remember this rule with spanning tree. You can't really go wrong. Lower is better. Lower wins. The reason why it picks lower is better, is because when it comes to distance, lower is usually better. Like if I've got two ways of getting to Galway, one way is going to be 200 kilometers and the other route is going to be 300 kilometers. Which path will I take? I'm going to take the one with lowest kilometers, because lower is better when it comes to distance. When it comes to time, lower is better. If I've got two ways to get to Galway, one route is going to I get there in 2 hours. The other way, I'm going to get there in 4 hours. I'm going to pick the 2 hour one. Okay. So here, the cost for B to get to A is out its direct connection. B can reach A via C, but it's 38. So it looks at this link here and looks at this link here and adds the two of them together. Any questions on that, guys? Okay, so when it costs, so if it costs B's best path is to A is out 0/0, C's best path to A is out 0/0, then your redundant connection is here. So any traffic between B and C has to go via A. Now, it's a bit misleading what I did there is because you don't delete the link. The link stays physically up. What happens is one of the switches will put the port into what's known as a blocking state. It will block traffic leaving and entering it. So which switch do you think is going to put the port into a blocking state? Is it going to be
Core switch. The core switch A.
No, because you can't remember all traffic
Sorry. Yes.
between B and C must go via A. So one of these, this is our redundant link here. So it's either this one here or this one gets blocked. The whole thing about the core switch is that it needs all of its active connections to be up. The switches with the highest bridge ID will be in blocking. So which is switch C? This here. Okay. This will put this port state will go, this port FA1/0 on switch C will go into a blocking state. It will not send or receive packets coming out of that port on FA1/0. So if you have switch 2 that sends a broadcast storm, it's not going to, switch C is just going to kill it there. It's not going to send it back out to A because then you'd have a loop. Okay. All right. Is there any questions on that, guys? We are going to be like, I mean, most of this evening we're going to be looking at Spanish tree. And because it is a complex topic, we need to go over it again and again and again. But it will, the more you get it, the more you go over it, some of it will kick in. It has to, hopefully. Okay, so when we have our Spanish tree election, we've got a number of different types of switches. Okay. A number of different types of ports. We know the first thing you do is elect the root bridge. That's always what you do first. Elect it. Well, the first thing, remember, this is all automatic. The switches elect the root bridge. You can set up these 3 switches, plug them in and walk away, and they will automatically do everything for you. You don't have to do anything. It doesn't require any manual intervention at all. Okay, so what will happen is the switches all amongst themselves, A, B, and C, will elect switch A as being the root bridge. Why? 32768, 32768, 32768. There's a tie. AAA is lower than BBB is lower than CCC. Switch says I am the root, or I am root. Sorry. Yeah. The root bridge. B says my best path back to A, because now it basically the root means the other switches must find their best path back to A, because it's all about finding their best path back to A. So B said my best path back to A is here. I just put a black circle around. C said my best path back to A is here. Then you have this redundant link that is not being used. In order for this link not to be used, either C blocks it or B blocks it. But because C has a higher bridge ID, C will put this port in a blocking state. Okay, So you got these 3 port types. You got the root port. The root port is the port the other switch is used to reach the root bridge. The root port is the switch, is the port the other switches use to reach the root bridge. Okay, so in other words, this is going to be a root port because that's the port B uses to reach the root bridge. Does that make sense? This port here is going to be a root port because that's the port C uses to reach the root bridge. The root switch itself won't have root ports because it doesn't need ports to reach itself. Okay, the root port is the other switches use the root port to reach the root bridge. Switch B will have a root port because switch B is using this port to reach the root bridge. Switch C's port here is used to reach the root bridge. Okay, and then you have your designated port. Designated port is your standard forwarding port. With a designated port, you must have one designated port per link. Okay, now there's a rule with the designated port. The root bridge's ports are always designated ports. This is a really good rule. You must have a designated port per link. Per link. Okay, now just think about it. If this is root port here, well, then it stands to reason that the other connection must be designated because you must have a designated port per link. If this is root port here, well, then the other side of the link must be designated because you must have one designated port per link. We go down to our redundant connection. We already have identified this port here as being blocking or blocking port. Blocking. Another one for blocking is alternate port. Alternate port or AP. So you kind of say it is an alternate port and it is blocking traffic. So if the one here is C on this one here is blocked, well then what's this port here called? What port type is that? Is it a root port? Is it a block port? Is it what port is it?
Forwarding.
It's a forwarding port. What type of port is it? Is it a root, designated, or blocking?
Blocking.
Designated.
You must have one designated port per link. See, we've got 3 links here. Link number 1, link number 2, and link number 3. We have a designated port on link number 1, which is a root bridge. We have a designated port on link number 2, which is a root bridge port. And then our designated port on link on connection number 3 is on BBBBB designated. You must, it's when you get used to that, it's a really helpful rule. You must have one designated port per link because it'll help you design your spanning tree network and being able to document your spanning tree network. Any questions on that, guys?
All good.
Okay, cool. Right, where are we? Where are we? Let's have a look at this one. Sorry guys, just give me 1 second here. Okay. That was 3 switches. Here's 4 switches. Now remember, I'm going to write down the steps, right? What happens first? Switches elect the root bridge. All the other switches must find best path back. Now, how do they find the best path? With the lowest cost. Any redundant link is temporarily disabled. Okay, first thing, number 1 is elect the root bridge. Okay, again, use the chat. I want to try and make this as sort of interactive as possible. So just to keep you awake and, you know, so use the chat. Let me know, try to keep you awake. Let me know which switch is the root bridge. Is it switch A or switch B or switch C or D? We've got 4 switches. Even before that, is there like, are we going to have a loop? Are we going to have a broadcast storm here, a layer 2 loop between our switches? Do we have a danger or have a loop?
Yes.
Yes. The way you remember having a loop is think of if a packet goes in one port or goes out one port and has the potential to come in on a different connection to the same switch, well, you're going to have a loop. So switch A sends a packet out FA0/1, and that packet will go in to switch A on FA0/2. Well, then you got a loop. It's just looping around. Okay, so based on that, what switch here is it's a root bridge? Again, use your chat there. Switch A or B or C or D? Good, good. Why not switch A? So what do we know about this switch here? About these 4 switches? What do they have in common, if you like?
The first 4 numbers in the range is all 0013.
For
The
6
same
numbers.
They're the same manufacturer.
001380, 001380, 001380, 001380. Same vendor, yeah, exactly.
Switch A looks like 8039 from where I am.
So 00138039 is the kicker. D7 is the kicker on B. 30 is the kicker on C. And C7 is the kicker on D. Which is lower? Switch C. All right. Any questions on that, guys?
No.
Right, okay, move on. Okay, so elect the root bridge. Okay, so switch C is the root bridge. Let's just okay. Now, all the other switches must find the best path back to the root bridge. So A, now remember what I'm going to put in, I'm going to put in the costs. So FA, fast Ethernet ports have costs of 19. Gigabit ports
4.
have costs of 4. Okay. FA cost of 19, gig ports have cost of 4. Okay, so what's A's cost? So all the other switches must find the best path back to the root bridge. Like C doesn't need to do this calculation because C is the root bridge. Why would it need to cost its, why would it need to calculate its cost to itself? Like if you're in Galway and if you're in Galway City, if you're in Ayr Square and you need to get to Ayr Square, do you find out how far does it get for you to go from Ayr Square to Ayr Square? No, because you're there already. So C doesn't need to find out its cost to get the root C, switch C, because it's the root. But A, B, and D need to find out the cost to get to C. I hope this makes sense. So what's the cost of A to get to switch C?
19.
Yeah, because it's fast Ethernet. What's the cost of D to get to C?
4.
Very good. Now, this can be confusing, right? The thing is, you do have a fast Ethernet connection on switch C. And you can only go as fast as your slowest link. But switch D doesn't take the actual speed of the link into question. Switch D just uses the bandwidth parameter and says you're a gig port, and then it cross-references that against its table. Gig port has a cost of 4. It doesn't look at the speed of the link. It just says gigabit 4, fast Ethernet 19. Even though in practice here, you can only go as fast as your slowest link, even though this link is 100 meg. Does that make sense?
Mm-hmm.
Okay, cool. So this cost is 4. Okay. Now let's remember our ports. So you got your root port, you got your designated ports,
Block port.
and you got your blocking port. Okay, so what port is this here on switch A?
Root port.
Root port, because it's the port switch A uses to reach the root bridge. Okay, so I'm going to put this down here as RP. I'll put on different colors. This is RP, root port. Okay, what port is this here?
Root port.
Root port, because it's port D uses to reach the root bridge. RP. What port is FA 0/1 on switch C?
Designated port.
Yes, why?
Because it's a designated port.
Because it is a designated port, and you must have a designated port per link.
Actually,
And the root bridges ports are always designated ports. Okay, and FA 0/2,
Same.
designated
port.
port, yeah, because you must have a designated port per link. Okay, switch B. What port is gig 0/1? Okay, well, even before we do that, we shouldn't be even looking at that yet. We need to find which is the best way for B to get to C. Which is the best way, which is the lowest cost path for B to get to C. If I've got two ways to go from Dublin to Galway, one is via Athlone, and it's going to be 200 kilometers, and one is via Kerry, and it's 500 kilometers. I'm going to pick the lower one because I'm going to get there quicker.
B goes through D, back to C.
What's the cost for B to get to C via D?
4. 8 in total.
Yes, very good. It's commutative. Well done. So it looks at this link here is 4, and this link here is 4. It's 8 altogether.
How does switch B know the cost of port 0/2 on switch D?
Switch D tells it. Great question.
Okay.
How does it tell it? It sends its BPDU message. So switch D goes, hey, switch B, let me tell you about my cost back to the root. It's costing me 4. And then switch B goes, oh, well, if it costs you 4 to get to the root and it costs me 4 to get to you, well, then my cost, I'm switch B in my head. Switch B's cost to get from B to C via D is 4 plus 4 is 8. Is that okay?
Sorry, Lee, on switch C, FA02 is a
Yeah.
fast. Does that not become 19?
So we are looking, so how it calculates it is switch D looks at its local port. Okay, so switch D says my cost to get to C is calculated based on D's local gig 0/2. Switch D won't know that this is a fast Ethernet port, and it won't use that as its costing system. It only looks at its local. Switch D does it like a show IP int brief on itself and says, oh, this is a gig port connecting to C. Gigabit uses cost of 4. It doesn't even look at the speed of the link.
Okay, thank you.
What about the other direction though? What about FA02 to G02?
Well, but C won't use, so all the other switches must find the lowest cost back to the root bridge. So
Back,
C doesn't
yes.
need to
Sorry,
reach
back.
itself via anywhere. It's basically, it's how what we're doing, what spanning tree is doing, it's finding out the best cost back to switch C. And it does that based with the intention, I have to block one of these ports. Okay, Philip, no problem. I have to block one of these ports, okay? So in order to do that, it basically says, well, which is the core switch? We're going to design our spanning tree network around the core switch, and then we can shut down one of these connections or temporarily block one of these connections. So that's what it's all about. So this whole costing system is basically, once we know the core switch, then we can work back from there. So switch B is costing, it costs switch B 8 to get to C via D. Does that make sense? 4 plus 4 is 8. What does it cost B to get to C via A?
B 423.
So you've got 4 here, and you've got 19 here. Yes, overall 23. Okay, so which is the best path for B to get to C? Is it via A or via D?
Via D.
Via D. So what's the, okay, so what port is this here then on gig 0/1?
Designated port.
It's the port that B uses to reach the root bridge. So therefore it's going to be the
Root port.
root port, yeah. So again, the definition of the root port is the port the switches use to reach the root bridge. This is the port B uses to reach the root bridge. If this is root port, then what's the other end here going to be?
Designated.
Designated port. Why? Because you must have one designated port per link. Okay. So where is our redundant connection?
FA02.
So it's a link between B and
A.
A. Okay. So remember, one of these ports gets put in blocking state. Is it A or is it B? Is it FA0/2 on A, or is it gig 0/2 on B.
I'd say
No,
gig
wait.
slash
Let me tell you, let me give you a clue.
the lowest.
The lowest, lower is better, but it's the switch that has the lowest bridge ID is considered a better switch. So switch A 00138039 is better than D7. So because of that, this here is blocked and this here is designated. Okay, so when there's a tie between this link here on switch A or this link here on switch B, because switch A has a lower bridge ID is just a number, by the way. Bridge ID is just a number. Because lower is better, 39 is lower than D7, this is blocked.
Would it ever go on the lowest cost?
No, because it'll always be in the event of a tie here. In this, no, well, it might go on the lowest cost in some other event, and we could probably look at a scenario here. But in this scenario here, it's going to look at
The Mac.
the Mac.
Mhm.
So if we have a PC connected to switch B here, okay, PC, and we got a PC connected to switch A, how are they talking?
Via D and C.
Via D and via C and up here. Yeah. You can't have this link, this link, this link, and this link active at the same time. You can't have those 4 connections active at the same time. If you do, you're going to have a broadcast storm. Okay. It's coming up to 25-2. We'll take 15 and come back at 10 to. I'm thinking about that for a second. Yeah.
Cool.
Okay, guys. Grab yourselves a cup of tea.
Good luck.
All right. Thanks.
Yep.
I'm going to pause the recording here. Here. So just to recap on that, let me just close that and open another slide here. Yeah, so you can see here, sorry, move that across. You can see here how the election process is happening. So the switches again, elect the root bridge. So you can see switch C, I'm the root, so my cost myself is 0. And then you can see the cost A's, switch A's cost is 19, switch D's cost is 4. And then switch B says, well, I've got 2 ways of getting to the root bridge. I can either go out gig 0/1, which is cost of 8, because you got 4 and 4 is 8, or gig 0/2, which is cost of 23, 4 and 19 is 23, but gig 0/1 is better. All right. And then we just select the port roles, which we've seen. C says it was the root bridge because it had the lowest bridge ID. So this was the root bridge here. Okay, and designated port. The root port was the port used to reach the root bridge. This is A's root port. This is D's root port. This is B's root port. Then you must have 1 designated port per link. This was our blocking port, our alternate port. Designated port per link. Okay. Any questions on that, guys?
No, all good.
Okay, cool. Right. Let's just close up there. And okay. So let's have a look at an example of this. Get packet tracer here, 1 second. One moment. So what I'll do is get you to open up packet tracer. If you go into day 7, isn't it day 7? I'm going to bring it up here now. So go to Dropbox, CCNA material, slide labs, day 7, go into labs and go into spanning tree lab here. We'll do this lab together. So this should bring up, there we go. When you open up this lab on packet tracer, you still see these 3 connections. What I might just do is open up 3 new switches, because these are old. Might be old switches belonging to a different lab. So let me just grab 3 new switches. Okay, so what I'm going to do, guys, is start off again with a blank. Okay, so just delete that there. We'll get 3 switches to start off. Just delete those 3. Get 3 switches. Okay, so let me know if I'm going too fast here. Okay, what we're doing is, and we're being recorded, we're going to get 3 switches: switch A, switch B, and switch C. Okay, so take switch A, use the 2960, B, and C. A, B, and C. Okay. And then we get a connections, goes down to connections, copper straight through. We're going from gig 0/1 to gig 0/1. Okay, I'm going to note them as I say 0/1 to gig 0/1. Okay, this is A. SWA, and this is SWB, and this is SWC. So gig 0/1 and A to gig 0/1 and B. And then we got B to C is going to be gig 0/2 to gig 0/1. Actually, now really by right, I should be using crossover cables. It shouldn't make a difference, but look, I'll just be pedantic. 0/1 to 0/1, 0/2 to 0/1, 0/2 to 0/1. And then from A to C, 0/2 to 0/2. Zero slash two to 0/2. Now, depending on what switch you made as A, B, or C, what we will do is we're all going to make switch A the root bridge. Okay, I know for a fact on my diagram A is not the root bridge. Actually, I can tell you straight away that out here, what switch has the lowest MAC address based on my diagram? I can't go off yours. Without even looking at the MAC addresses. What switch is the lowest MAC?
Switch A.
Sorry? A, B, or C?
A.
What switch is the root bridge?
B.
B is the root bridge. Yeah. So B will have the lowest. How do we know B is the root bridge? Because A here, this 0/2 on A is blocking. You can see the port is amber. So it tells us that it's blocking. So if this is blocking, that means A, we know B is the root bridge because the two connections back to the root bridge is active, active and active. The redundant link is between A and C. A is blocking, so that will tell us that A has a higher MAC address than B or C. Does that make sense? Are there any questions on that there?
Nope.
Okay, so what we want to do is we're going to make A the root bridge. Now, why would you make A the root bridge? Well, the thing is, you should be in charge of your own design. You should be able to design your network the way you should want it to be. But usually you will have the best switch as being the core switch, and the other connections will have a connection back to that. So the best switch here is going to be switch A. Okay, so how do you make switch A the root bridge? You click on it, go into enable. What I'm going to do is I'm going to give my switches host names. A, I'm going to B here. I'm going to C here. So I've got my three switches with host names A, B, and C. Okay, we're going to make A switch A root bridge. So big space T, spanning tree, VLAN 1, priority, and there you go. Set up a bridge priority in increments of 4096. If I want A to become the bridge ID, remember you can't change the switch's MAC address. The default priority is 32768. Okay, you can't change that. You can't change AAA or BBB or CCC here, but you can change the priority value. So if I change the priority value on switch C to become 0, well then in this case here, in this diagram, switch C will become the root bridge because 0 CCC is lower than 32768 AAA and is also lower than 32768 BBB. Does that make sense? So spanning tree VLAN 1 priority 0. And you can see what's happening. Look, spanning tree is kicking in, it's changing the port types. Gig 0/2 wasn't blocking, but now what's happening is it's getting demoted or promoted, and this one here is put in a blocking state. Just fast forward the time. Okay, so it's time to start writing in our ports or typing in our ports to see. To find out your port types, one command. So if we log in here into switch B, I want to find out my port types. If you want to find out your spanning tree information, show span. Show spanning tree, show span. Okay. So you can see here, it gives us two pieces of information. Let me just close that there. Information about the root ID and information about the bridge ID. Okay. Trying to get both of these in. So I'm on switch B here. This is switch B. The root ID is information about the root bridge. Okay. I'm logged on to switch B. The root ID is information about the root bridge. The bridge ID is information about the locally connected switch. So we are connected to switch B. The bridge ID is information about the switch that we are connected to, which is switch 2, switch B. What is the MAC address of switch B?
.98DE.
98DE, yeah, the 0030 is the MAC address. And if you look here, right, switch A is the root bridge, but it's a root bridge because its priority is much lower than switch B. But it has a much higher MAC address. 00D0 is higher than 0030. Now you're probably asking, we changed the priority of switch A to be 0. Well, then why is the priority coming up as 1? Well, what spanning tree does is it takes the VLAN ID, which is VLAN 1, and it adds it onto the priority value. So 1 and the priority value was 0, but then the priority changes to 1. The bridge ID was 32768. It adds VLAN 1 onto that, so it becomes 32769. And you got your ports down here. Okay, so let me just use, I'm not going to annotate this here, drawing. So you can see your ports. So gig 0/1 is a root port. This is information about switch B here. So we'll put in the MAC address of switch B. What I'll do is I'll use the first 4 characters. So switch B's bridge ID is 0030. Switch A's MAC address is what? 00
0D0.
D0, yeah. 00D0. That's a D. The port numbers, gig 0/1 is root port on B. Because that's the port B uses to reach A. Remember, A is the root bridge. How do we know what the root bridge it tells us? How do we know actually? A is the root bridge. How could we tell by looking at this that A is the root bridge? The simple fact is when you see gig 0/1 here with root, that's the port used to reach the root bridge, and the cost is 4. Okay, so that's yeah, so just yeah, okay, cool. Okay, so that's root port. Then we can tell even so designated port gig 0/2 is designated port, so we put DP here. We know on C we can see packet tracer is great because it shows us here this is blocking. block port, yeah. What's this one here on C, 0/2 on C then?
Root port.
Yes, because it's a port C uses to reach the root bridge. What port is this?
Designated.
Designated port, because it's the root bridge's ports are always designated port, and then this port here is designated port. That's it. So we designed our spanning tree network. We didn't do any of this. The only thing we did was we changed the root bridge to switch A. How did we change the root bridge to switch A? Is we gave it a priority of 0. But when you add VLAN 1 on the priority of 0, it becomes priority of 1.
And VLAN 1 is always the native VLAN, even in
VLAN
spanning
1
tree.
is the default VLAN. Yeah. Yeah. The default one. Exactly. So if we log on to switch C here and exit, show span. Now remember, switch C will also show us. Let me just see if I can just put this into WordPad. It might be easier, or into TextPad. Let me just make this a bit smaller. Just 1 second, trying to make this a little bit easier to understand. So this is switch C, okay? So in switch C, you can see here. And what's the MAC address of switch C?
Zero 0060.
Yes. So the bridge ID is information about the local switch, whatever we're connected on. I was meant to say local, LOCAL, see in there. And the root ID is information about the root bridge. We know switch A is the root bridge. So once it says the root bridge, this is switch A's MAC address. So you see switch A's MAC address if I log on to A, C or B or A, because it'll be under root ID. We are connected to switch C. So the local bridge ID is information about switch C. Now the priority is 32769. I'll talk about this the timers now in a minute. Then you look at the ports. Gig 0/1 is alternate. The role is alternate, but the status is blocking. It's blocking traffic. Gig 0/2 is the root port, and that is the port that switch C uses to reach the root bridge. All right. Okay. So I'll log off that one there. I should do that there a second, and I'll go into switch A. And I'm going to copy this into Notepad because I think it's easier to look at it in Notepad. Switch A, show span. Check. So here. Okay, so how do we know this is the root bridge here?
The MAC addresses are the same.
The MAC addresses are the same. What else?
All ports are
Uh,
designated.
Gig,
All
gig
ports.
gig 1
Yeah,
and gig
and
2.
And you probably missed the most the easiest way of knowing this is the root bridge.
This bridge is the route.
Yeah, exactly. Does exactly what it says in the tin. Yeah. So the priority, so the MAC addresses are the same because we're connected to the root with switch A, and the switch A happens to be the root bridge. So the MAC addresses will be the same. The gigabit ports are designated ports. And yeah, this bridge is a route. So it's always a good idea if you're doing, you know, to map out your spanning tree network. If you've got multiple switches connected to trunk connections using redundancy, to even have a map, something like something, obviously this is a bit just thrown together, but something like that. Because if you have an outage or an issue and you have to troubleshoot, it's much easier to troubleshoot a broadcast storm or something happening when you have a map that you can refer to, when you know the flow of the traffic. Is that all right?
Yeah.
Cool. Okay. We'll just clear this here. Okay. So what I'm going to do is I'm going to connect in a PC into switch B and the PC into switch C. Okay. And in here, 0/2 and 0/3. Okay, I'm going to give this one here. I can give this one an IP address of .2 and this one an IP address of .3. Okay, so let's go in here. I'm going to go in here, and so this PC is going to have the IP address of 192.168.1.2, and this one here is going to have the IP address of 192.168.1.3. Okay, so let's run a ping. Now, you're not going to tell how, you see, with switches, you've no way of knowing your path to get from switch B to switch C. If these are routers, you could do a trace route, and the trace route would show you your layer 3 hops, but there's not, they're switches, so we don't know. But if I log in, go to command prompt and ping space -T 192.168.1.3. Okay, so it's running a ping. Now, what I'm going to do is I'm going to show you, before, while it's running that ping, I want to talk about the different types of ports that we have. Okay, so at the moment it's blocking. So if a link goes down, say if this link goes down here between okay 0/2 on C, what will happen is C, this port that's in blocking, is going to have to go from blocking to, because it's currently in blocking, it's going to have to go to forwarding. But it doesn't go from blocking to forwarding straight away. It goes blocking, listening, learning, and forwarding. It can stay in blocking for 20 seconds, up to 20 seconds. Listening. So what happens is when this port 0/1 will start listening out for BPDUs. It can stay there for 15 seconds. Then the port will start learning the MAC addresses, populating the MAC address table. It can stay there for 15 seconds. So how long can it take for this port to go from a blocking state into a forwarding state? 50 seconds. It can take up to 50 seconds for this port to go blocking, listening, learning, forwarding, which is a long time. Okay. Blocking to listening to learning to forwarding. Let me show it to you. What we'll do is we're running a ping already from switch B to switch C. What I'm going to do is, as we're running that ping, you can see it running, yeah. I am going to bring down, let's say 0/2 on A. So at the moment, traffic between B and C is going via A and down. You can see that. This is the great thing about Packet Tracer, is because you can see the amber link. We know that's blocking traffic. So it's going across into A and down across into C. So traffic between, so you're going, traffic here is going into A and A is sending it down here. Has to be like that. Okay. Does that make sense? So what we'll do is try and make this a little bit easier. Let's have it like that. Okay, so I'm going to open up here, and you can see the packets there. It is pinging, and so I'm going to go into switch A, and I'm going to gig 0/2 on switch A. Big space C. Actually, what I'll do is I'll go into C and bring down this link, because I want to see this link progressing. I want to see 0/1 going from blocking into listening, into learning, into forwarding. And what I'm also going to do is I'm going to get a clock stopwatch. Clock. Stopwatch. I'll leave that in the background. I'm going to bring it over shortly. Okay, and time it. It's not very scientific. Config space T. Okay, so I'm going to go into interface gig 0/2. Yeah. Interface 0/2. And I'm going to say shut down. Okay. I press enter, and as soon as we're going to press enter. Okay. So you can see the stopwatch. You know, I have the stopwatch running there. So you can see it's gone in here. Now what's going to happen? Let's go back and do show span. We want to keep an eye. Oh, it's gone into listening. We show span again. It's gone into learning, 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 forwarding. Oh, 30 seconds. And we should have traffic coming back up shortly. Or have we? There we go. So it was about 40 seconds there. So the port went from blocking to listening to learning to forwarding. Takes a long time. What will happen, and you can see it's pinging now, what will happen if I do this? Go back here into C and config space T and go into interface gig 0/2 and I do no shutdown. Well, what's going to happen? We're going to have another outage. While the ports realign with themselves, and because you remember, the thing is, switches always have to err on the side of caution. The switches have to say, okay, we're going to bring down everything until we have established that one of the ports is in blocking. And then as soon as we establish that, we can bring it back up. Because the end of the day, we can't have a broadcast storm happening on a network. It is better that no traffic gets through and we find out everything and we discover all our ports and use these BPDUs to map out everything, then have a broadcast storm. Okay. Another way. So let's say we're running a ping here, okay? And you can see the ping running. And let's say we have this guy here, this PC. And this PC connects into 0/10. What happens? Look. It's still amber. We've got a PC that I connected into switch C, and switch C is 0/10 is amber. What's wrong? Why isn't it coming up? Look at 0/10. What's it doing? It's learning. Now it's forwarding. What happened was 0/10, this port here, took about 34 seconds for that link to come back up. Why? Because let me just use Paint here for a second. Okay. When we connected this port here to switch C, switch C doesn't know what type of link this is. Now this is a laptop. This is an access port. We don't have broadcast storms happening on an access port. Why? Because it's an end device. You only have broadcast storms happening on devices that have 2 NICs, because then you have your loop. So you don't have a broadcast storm here. But the switch C doesn't know that. So what switch C is doing is this port is going into listening, into learning, into forwarding state before it comes up. Does that make sense? So when you connect a device into a switch, the port will be amber for about 30 seconds, 34 seconds, while it goes from listening to learning to forwarding. It's not that the switch is slow, it's the switch is always erring on the side of caution. Now there is a thing called port fast. And what port fast does is it disables spanning tree on access ports. So it will disable spanning tree on, let's say, 0/5. So if I go into 0/5 and I say I want to enable port fast does exactly what it says on the tin. It means the port will come up fast. How does it make the port come up fast? Because it disables spanning tree checking. So instead of having listening, learning, forwarding, it just comes straight up. Does that make sense? Let me show you. Let's connect this into 0/5. Make this into 0/5 and go back here. Backface T, interface FA 0/5, spanning tree, port fast. Okay. And it says, warning, port fast should only be enabled on ports connected to a single host. Well, this is a single host, such as a laptop. Connecting hubs, concentrators, bridges, switches to this interface when port fast is enabled can cause temporary bridging loops. Use with caution. Port fast should only be configured on FA0/5, but will only have effect when the interface is in a non-trunking mode. Will only work when the interface is in an access mode. Okay, so what you're doing is, instead of earlier on, again, I'll go back to this, earlier on, we had a problem with switch C. FA0/10 took so long to come up because it went through your blocking, listening, learning, forwarding stage. Let's try 0/5. Let's unplug it and plug it back in. What? Green, straight away. What was 0/6? Amber, 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 amber. Why? Listening, 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 listening. Learning, learning, learning. 0/6, you can see it there. Learning, 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 learning. 20 seconds. There we go, 15. So yeah, so sorry, 20 seconds of blocking, 15 on listening, and 15 on learning. 15 on listening and 15 on learning before it goes in. Yeah. So 0/5 comes up straight away. Any questions on that, guys?
No.
Okay, so just to recap on that one there. So this is what happens when when we're not running normal spanning tree. Spanning tree, the port stays in blocking and can stay in blocking for 20 seconds. It's called max age before going into listening phase. It can stay in then it goes into listening, where it can be in listening for 15 seconds, goes into learning for 15 seconds, where it's learning MAC addresses and populating the MAC address table, and then it can go into forwarding state. That takes a long time. The solution is rapid spanning tree. Okay, what rapid spanning tree does is the ports come up much faster, or STP. Okay, now what you need to do is, really to be efficient, we plug, I'm making this one here, port fast 2. Okay, I'm going to try and make this as efficient as possible. So this link here is connected to 0/2, and this link here is connected to 0/5, right? 0/2. So I'm going to turn on port fast over here. See, look, it's taking a while already. So I'm going to go into B, enable, big space T, interface FA 0/2, Spanish tree, port fast. Comes up because straight away it comes up. Okay, so I want to enable rapid spanning tree on all of my switches because it's much faster. What did we have with it? It took 50 seconds or 50 seconds the last time. To turn on spanning tree or rapid spanning tree, you say spanning tree mode rapid. You have to do it on all 3 switches. So on B, spanning tree mode rapid. On A, go into A, enable, big space T, spanning tree mode rapid. On A, and on C, the same thing. Big space T, spanning tree mode rapid. I better connect this into 0/5. Now, how do you know what mode you're going to be in? And if I do show span, rapid spanning tree, it'll say RSTP. RSTP, rapid spanning tree. With normal spanning tree, it'll just say IEEE. That's normal spanning tree there. IEEE. Rapid spanning tree, RSTP. Okay, very important to know the difference. You could get asked an output from a screenshot that says this, and it will ask you what type of spanning tree is, what version of spanning tree is running on this switch. RSTP, rapid spanning tree. IEEE, normal spanning tree. By the way, rapid spanning tree is 802.1W. Okay, so normal spanning tree, just STP in its own, is IEEE 802.1D, whereas RSTP is 802.1W. Okay, all right. So let's compare and contrast rapid spanning tree with normal spanning tree. So again, I'm going to go into switch PC here. I'm going to run a continuous ping. Oh, we're running it anyway. Okay. And I'm going to go into C here, and I'm going to disconnect one of the links. So if I do show span, so I'm going to disconnect 0/2. The last time we did this, we're running normal spanning tree. It took 40 seconds, at least 40 seconds. Backspace T, interface FA 0/, or sorry, interface gig 0/2, shut down. Now watch what happens. This amber port was amber for 40 seconds. It should basically come up straight away. Should go green straight away, hopefully. There we go. It's gone green. Did we have any outage? No. Look. Went from red to green straight away. No issue. Span. Gig 0/1 is in the root port because gig 0/2 is not there anymore. If I bring it up, backspace T, interface gig 0/2, no shutdown. Let me just stop this ping from running again. Hold on. And rerun it. Gig 0/2, do no shutdown. Oh, this take a little bit longer. One miss ping. One miss ping. See the difference? Massive difference. Like if I'm let's keep this here. Let's try and have this in the background pinging. So you can see here, yeah. And let's just unplug this guy. Much quicker. So that's definitely something you should do. Most switches now, most modern day switches will support rapid spanning tree by default, but if you get like a 2950 switch, it could be still running older spanning tree. So it's a no-brainer. Find out what switches, what version spanning tree you're running and run it on that. Does everyone stay with me on that? Okay. What I'm going to do is, and this is going to be I want you to do this for your homework as well, is using this lab. Let me do it here, and I'm going to go through it and give you all a chance to do it then tonight or during the week. We're going to cause a broadcast storm. Okay. So we have all our setup, our switches set up. What we want to do is cause a broadcast storm. Now, in order to cause a broadcast storm, there's a few things we need to do. I'm going to document them now. I'm just going to write them in. So what we need to do is we need to disable spanning tree checking. Disable STP checks. How do you disable spanning tree checks? I just talked about it 15 minutes ago. By enabling port fast. Remember, port fast means that the switches won't be doing blocking, listening, learning, forwarding. They're going to come up fast. How do they come up fast? They come up fast by not checking for listening, learning for your BPDUs. Now, port fast will only run on access ports, such as PCs. So what we need to do is we need to disable spanning tree checks in on our trunk ports. But it says by enabling port fast. But port fast won't work if these are set to trunk links. So we have to configure our trunk links as access ports. You have to work hard to cause a broadcast storm. Port fast will not work on trunk links. So you have to configure them as access ports. Does that make sense? And then we have to disable spanning tree globally. And this has to be done on all 3 switches. So we have to turn off spanning tree, the whole feature, on those 3 switches. Okay. So any questions on this? Now, this is not something that you're going to do in a network environment. You're never going to have to do this on the network environment. Okay, unless you didn't get a pay rise or something like that. You wanted to cause a lot of damage. There's easier ways of bringing down your network than doing this. Just go into the comms room and start unplugging cables. That's the best way. Actually, don't. I'm not telling anybody don't go plug labels. It's the fastest way to get sacked. Not only get sacked, probably end up in jail. And depending on the company you work for. I know if with my company I work for, I'll be prosecuted. So yeah, don't do that. Okay. So let's do it. Okay, go into switch B. Config space C. How do you configure 2 links at the same time? So what do we want to configure? We want to configure our trunk links. So we can use an interface range gigabit 0/1 space hyphen space 2. That means we can configure these 2 trunk links at the same time. What do we need to do? We said we need to configure these as access ports. Because if I type in switch port fast, switch port spanning tree port fast. It says it won't work because it'll only have an effect when it's in a non-trunking mode. So switch port mode access spanning tree port fast. There we go. Okay, there's B done. Let's go into A. Oh, sorry. I need to do another thing on A and B. What do I need to do? No spanning tree VLAN 1. I have to disable globally. Switch A is done. And go, oh, sorry, switch B is done. Go to switch A, enable, fixed space T, interface range, gig 0/1 space hyphen space 2. What do I need to do? Switch spanning tree. Actually, we'll do switchport mode access first. Switchport mode access, spanning tree, port fast, no spanning tree, VLAN 1. Switchport mode access, spanning tree, port fast, no spanning tree, VLAN 1. And I go with the C and do the same thing on C. Exit, interface, range, gig 0/1 space hyphen space 2, switchport mode access, spanning tree, port fast, no spanning tree, VLAN 1. And let me just do something. Let's cause a broadcast storm. Run a ping. What's happening? Can you see that there? I don't know if it's clear.
Yeah, you can see the loop.
You can see it there.
Yeah,
It's
changing it.
lighting up like a Christmas tree.
Yeah.
And is any packets getting through? No. Request timed out. Because the broadcast messages are going so fast, around and around and around and around, nothing else is getting through. What if I go into this here? Into switch this guy here. Ping 192.168.1.2. Nothing. Yeah. So we're having problems. Okay, so here's the scenario. Oh, we got one ping came through. So like the odd ping will come through because basically, you know, it's kind of like a DDoS attack, distributed denial of service attack. You're just flooding the devices with so much packets that it's just getting overwhelmed. But the odd one will get through. That's quite a lot, actually. I'm surprised. If this is a real switch, you wouldn't see that many. You'd see, geez, you might have 1 out of 1,000 pings getting through. But still, that's like you can't have a functioning network like that. So there's a scenario. It's coming up Paddy's St. Patrick's Day weekend, and your lads are out having a few pints, and it's a Friday evening, and you're about to join them in the pub, and you're walking out, and your boss calls and goes, "Up, Graham or Edmund or John or Liam, Richie, Pablo, Tony, come back, fix this problem. We've got a broadcast storm happening on the network. You can't leave and go to the pub unless you fix this issue." So you go down to the comms room and you have a look. What are you going to do?
Drop off one leg.
Yes. Disable, remove your redundant connections. The reason you're having a broadcast storm is because
They're all
you have
connected.
multiple connections. You got the 3 active links at the same time. So drop your redundant links and everything should click back into place. So we'll remove this guy here. Let me just hold on, get this link here. Go. Fast forward a second. And there we go. Everything is working. So so you solve your immediate issue. You're having a broadcast storm because there's some sort of a loop on your network. Spanning tree is clearly not working. You don't have to go and enable spanning tree and find out what the problem is. Just get rid of your redundant link. It's better to have a network set up like this that has no redundancy but is working than a redundant network where nothing is getting through. Okay. Any questions on that, guys?
No, all good.
All right. Okay, cool. Just give me 1 second here. Just want to have a look at connections here. Just doing it in another lab. So definitely, if you get a chance to do that, just build your own. So your homework would be to, here it is here, like do that, set that up. Because your 3 connections, switch A, switch B, and switch C. Give your switch host names. Give make A the root bridge. And always make sure that it's connected the proper way. And then map out the MAC addresses and port numbers for all 3 switches. But basically just going in and doing a show span. And then do what we did there, connect the laptop into B and the laptop into C and run it across, see how long it takes, and then enable rapid spanning tree. Do you remember how to enable rapid spanning tree? So let me just cancel this. To enable rapid spanning tree mode rapid. And you can set that back up. Then you can cause a broadcast storm. There's the commands that cause a broadcast storm. Or STP, exactly. Okay. Now I want to bring up a lab here because I think it's important. I just want to show you how the switch kind of looks at the differences between an access port and a trunk port. Okay. So the way I've kind of done this is that we're all in the same VLAN. Okay, we've got 1.1, 1.2, 1.3, 1.4, 1.5, and 1.6. And if you see the MAC addresses, okay, so 1.1 is connected to 0/1, I believe. Just check that out. Yeah, 1.1 is connected to 0/1. 1.2 is connected to 0/2. 1.3 is connected to 0/3. 1.4 is connected to 0/4 on switch B on the other switch. 1.5 is connected to 0/5 on switch B. 1.6 is connected to 0/6. So just for the purpose of demonstrating this, I'm actually this either goes really, really big or really small. I've matched the physical port on the switch to the IP address. Okay, now they're all on the same VLAN, so you wouldn't have to worry about a trunk link here. So let's just look at, I'm going to use 1/3 as an example here. Okay, so let me just use this annotating, draw this here. Okay, so 1/3, let's say we want to ping. /6, okay? So the source MAC address is 6E98. Now we're pinging 1/6. So source IP address is 1.3, destination IP address is 1.6. Now, if this PC here has never pinged 1.6 before, it's not going to know the MAC. So it's going to have to send an ARP. ARP, what is the MAC address of 192.168.1.6? Now, this packet will come into switch A on port 3. Yeah. Switch A will update its MAC address table to say that I have received a frame coming into me on port 3 with a source MAC address of 6E98. Okay, now that ARP will be a broadcast message. And the switch will send it at all ports, including the trunk link. This frame comes into, let's say this port, let's say this is port number 9. I don't know what port this is. This frame will come into switch port B on port number 9. Switch B here says, I've received this frame coming into me on port number 9. What will switch B put down in its MAC address table? Switches update the MAC address table based on the source MAC address of the incoming frame, which in this case is 6E98. Okay, which is the source. So switch A will not manipulate the source MAC address or the destination MAC address in any way. Switch A is just sending this frame over to switch B. Switch B receives this frame here with this MAC address on port 9. So it says, I have received this frame coming into me on port 9 with a source MAC address of 6E98. Now the destination tells switch B to send it out all ports. So it'll send it out port 4, port 5, and port 6. This device here wants to respond back to A because it's looking for the MAC address of 1.6, and this is 1.6. So the response back is going to be, source will be 3C09. The destination is going to be 6E98. Okay. So I'll put the destination in red. So this is going to go into switch. Let me just clean off some of this stuff here. Let me put the destination here. So this is going to go back in to switch B. Switch B is going to say, oh, the source MAC address of 0/6 is 3C09. And then it's looking at the destination and go to 6E98. Oh, I'm going to send it over here because it has already identified 6E98 with 0/9. It comes into switch C or switch A here. Switch A will say, oh, you're going to 6E98. Let me, oh, I know 6E98 is 0/3, and we'll send it over. So what you're going to see is on the MAC address table for each switch, on the MAC address on this port here, this trunk link, you're going to have the MAC addresses of this port, and this port. Because when they're sending packets across, when A is receiving packets from 1.4 or 1.5 or 1.6, the source MAC address will be 8A44 or 4946 or 3C09. Because switches update their MAC address table based on the source MAC address of the frame. Does that make sense? We have a look. It's easy to do it. We just go in here and we run pings. So I'm just going to run a ping to 1.3 ping space minus C 192.168.1.6. Okay, leave that running. This is going to be pinging 1.5. Ping space minus C 192.168.1.5. I just want to keep these pings running so we can keep the MAC address table current. Ping 192.168.1.4. Okay, so leave that running. Go into switch A. And have a look at the MAC address table of switch A. Enable show MAC address. Okay, so our trunk link is 0/24. But if you have a look, we can see our local MAC addresses. 0/1 is 3073, or sorry, 307C. 0/2 is 353C. And 0/3 is 1698. But all the other ones are frames that switch A has received from switch B on the trunk port. Because switches update their MAC address table based on the source MAC address of the incoming frame. So if this guy here is coming across, switch A will say, you're coming, I'm just receiving, so this is 0/24. 0/24. And this is switch A. And this is switch B. Okay, does that make sense? So 8844, 4946, 3909, and AE18. Where's the AE18? That'll be the actual MAC address of B talking to A for using BPDUs or CDP. That will be the management MAC address. So switches have one MAC address of themselves, which is for management purposes. Any questions on that, guys? I'm very quiet.
Oh, good.